Maxima and minima of functions of two variables. A function f of two variables is said to have a relative maximum at a point x0, y0 if there is a disk centered at x0, y0 such that f of x0, y0 greater than or equal to f of xy for all points xy that lie inside the disk, and f is said to have an absolute maximum at x0, y0 if f of x0, y0 greater than or equal to f of xy for all points xy in the domain of f. Now we will see the definition of relative minimum and absolute minimum. A function f of two variables is said to have a relative minimum at a point x0, y0 if there is a disk centered at x0, y0 such that f of x0, y0 less than or equal to f of xy for all points xy that lie inside the disk, and f is said to have an absolute minimum at x0, y0 if f of x0, y0 less than or equal to f of xy for all points xy in the domain of f. So these are the definitions of relative extrema, relative maxima, relative minima. Similarly, absolute extrema, absolute maxima, absolute minimum. Now we can see extreme value theorem. If f of xy is continuous on a closed and bounded set R, then f has both an absolute maximum and absolute minimum on R. So from the figure, a surface is shown here. Now we can see that the point B corresponds to the relative maximum point and the point D corresponds to the absolute maximum point. In a similar way, the point C corresponds to the relative minimum and the point A corresponds to the absolute minimum. For finding the relative extrema, what we have to do is, if the function has a relative extremum at a point x0, y0, and if the first order partial derivatives of the function exist at this point, then equate the first order partial derivatives to 0. Now we will see the definition of a critical point. A point x0, y0 in the domain of a function f of xy is called the critical point of the function if the first order partial derivatives both equal to 0, or if one or both partial derivatives do not exist at the point x0, y0. For finding the relative extrema of functions, we are using the second partial test. Then it states that let f be a function of two variables with continuous second order partial derivatives in some disk centered at a critical point x0, y0, and let d equal to fxx at x0, y0 into fyy at x0, y0 minus fxy at x0, y0 the whole square. If d greater than 0 and fxx at x0, y0 greater than 0, then f has a relative minimum at x0, y0. This fxx is also denoted by the letter R, and fyy is denoted by the letter T, and fxy denoted by the letter S. That is, D is equal to RT minus S square. Okay, that notation also we are using in some textbooks. If d greater than 0 and this fxx at x0, y0 less than 0, that is r less than 0, then f has a relative maximum at x0, y0. If d less than 0, then the function has a saddle point at x0, y0. If d equal to 0, then no conclusion can be drawn. Now we can see certain examples. Locate all relative extrema and saddle points of the function f of xy equal to 3x square minus 2xy plus y square minus 8y. So for finding the solution, first of all find the first order partial derivatives. So fx at xy equal to 6x minus 2y, fy at xy equal to minus 2x plus 2y minus 8. Now equate these first order partial derivatives to 0. Solving these two equations, we will get x equal to 2, y equal to 6. That is 2, 6 is the only critical point. Now we can apply the second partial test. For applying the test, we need the second order partial derivatives. So fxx at xy equal to 6, fyy at xy equal to 2, and fxy at xy equal to minus 2. That is, this is the, we can in symbols r equal to 6, t equal to 2, s equal to minus 2. So d equal to r t minus s square, or fxx fyy minus fxy square. So calculate d, we will get as 8, which is greater than 0, and fxx equal to 6, or small letter r equal to 6, which is greater than 0. So if d greater than 0, r greater than 0, that shows that according to the second partial test, the function has a relative minimum at the critical point 2, 6. Now we move on to second example. Examine the function x cube plus y cube minus 3axy for maxima and minima. A can be positive or negative. Here find as usual the first order partial derivatives. So fx equal to 3x square minus 3ay, fy equal to 3y square minus 3ax. Now equate this first order partial derivatives to 0. Then we will get, equating this first order partial derivatives to 0, we will get two equations, x square minus ay equal to 0, y square minus ax equal to 0. Substituting one in other, or put y equal to x square by a in the equation x square minus ay equal to 0, we will get x raised to 4 minus a cube x equal to 0. Take x outside, x into x cube minus a cube equal to 0. Then solving, we will get x equal to 0 and x equal to a. And y equal to, substitute this in the y equal to x square by a, we will get y equal to 0 and y equal to a. So the stationary points or critical points are 0, 0 and a. Now calculate the second order partial derivatives. That fxx equal to 6x, fxy equal to minus 3a, and fyy equal to 6y. Then substitute all this in this formula, d equal to fxx fyy minus fxy the whole square, that equal to 36xy minus 9a square. Now we can find the value d at each critical point or at each stationary point. So at 0, 0, we will get d equal to minus 9a square. Then whatever will be the value of a, minus 9a square is less than 0. That indicates the function has saddle point at 0, 0. Then we will see at the second point a, d equal to 36a square minus 9a square, that's equal to 27a square, which is always greater than 0, whatever be the value of a. Therefore, f of xy has an extremum value at a. Now fxx equal to 2a. Then depending on this a, we can see whether we are getting maximum, relative maximum or minimum. If a greater than 0 and if a greater than 0, fxx equal to fxx is greater than 0, that means r greater than fxx notation is r, it will get greater than 0. Then we know that d also greater than 0, so that the function has a relative minimum value at a. And if a less than 0, we can see that this fxx, its notation is r, which is less than 0, and d also, but d greater than 0, which indicates that the function has a relative maximum at a. Now we move on to the third problem. Consider the function fxy equal to y square minus x square whose graph is the hyperbolic paraboloid shown in the figure. Find the first order partial derivatives, that is fx equal to minus 2x, fy equal to 2y. Then equate to 0, we will get x and y equal to 0. Then calculate d, we will get d equal to minus 4. That shows the function has saddle point at 0, 0. So from the figure, the surface shows this f of xy equal to y square minus x square. That is the surface shown here. Then at the point 0, 0, the function has neither relative maximum nor a relative minimum. Finding absolute extrema on closed and bounded sets. If f of xy is continuous on a closed and bounded set R, then the extreme value theorem guarantees the existence of an absolute maximum and an absolute minimum of function on R. These absolute extrema can occur either on the boundary of R or in the interior of R. But if an absolute extremum occurs in the interior, then it occurs at the critical point. So, for finding the absolute extrema, the following are the steps. Step 1. Find the critical points of the function that lie in the interior of R. Then step 2. Find all boundary points at which the absolute extrema can occur. Step 3. Evaluate the function f of xy at the points obtained in the preceding steps. The largest of these values are the absolute maximum and the smallest is the absolute minimum. Now we can see an example. Find the absolute extreme of the function f of xy equal to xy square on the closed and bounded set R, given by x greater than or equal to 0, y greater than or equal to 0, and x square plus y square less than or equal to 1. For finding the solution, the closed and bounded set R is given in the figure. The critical points, for finding the critical points, we can evaluate the first order partial derivatives and equal to 0. So fx at x0 y0 equal to 0 and fy at x0 y0 equal to 0. So from the problem, fx equal to y square, fy equal to 2xy, then equate to 0, we will get y equal to 0. Then when we equate fy equal to 0, then there are two possibilities, x equal to 0 or already y equal to 0, then x can be equal to a value a. A can be any value. In the given problem, you have a equal to 1. So the critical points are 0, 0 and 1, 0. Then now on the boundary of the circle, x square plus y square equal to 1. We can put y square equal to 1 minus x square. Then f of xy equal to xy square. Then replace y square by 1 minus x square. We will get x into 1 minus x square, that is x minus x cube. Now f of xy is a function of a single variable x, and we can denote this as g of x, that is g of x equal to x minus x cube. Now to get its critical point, we can find the first derivative. We can find the derivative and equate to 0. So dg by dx equal to 0. That implies 1 minus 3x square equal to 0. So x square equal to 1 by 3, x equal to plus or minus 1 by root 3. So y square equal to 1 minus x square. Substituting, will get y equal to plus or minus 2 by 3, plus or minus root of 2 by 3. Since x, y values are both greater than 0, the critical points are 1 by root 3 and root 2 by 3. Hence, in the given closed and bounded unit circle, the critical points are 0, 0, 1, 0 and 1 by root 3 root of 2 by 3. Then we can evaluate the function value at each of these critical points. So at 0, 0, function value equal to 0. At 1, 0, function value equal to 0. At the point 1 by root 3 root of 2 by 3, the function value equal to 2 by 3 root 3. From the above table, we have the absolute maximum at 1 by root 3 root of 2 by 3 and absolute minimum at the points 0, 0 and 1, 0.